Welcome back to another Valar Atomics update. Mark, where are you at in the world today?
I am in Pretoria, South Africa, where we have a team working, and I can't wait to tell you a little bit more about it, right?
Amazing. Yeah, let's talk about that just in a little bit. But first, we've had a couple exciting updates since we last talked. We have been working on our nuclear test site out in the Utah desert. It's beautiful, Emery County, Utah, at Valar Atomics at San Rafael, which is our test site. So we've had some construction progress on the site. Mark, do you want to give us just a little bit of update on what we've been up to out there?
Yeah, I mean, our teams are now fully mobilized to site. We are in sort of full speed construction. We started basically with our construction partner, Kiewit, preparing the site. We're working up towards having the concrete in place in the next couple of weeks. Really, the most exciting thing there, of course, is we've been blasting, and blasting is cool.
Blasting is really cool. And I've definitely sent a couple of pictures to my friends with the caption, anyway, so I started blasting. And I'm sure that we could put the meme in there as we play the video. But here's a little clip of us blasting out on our site.
You joke about that, Isaiah, but I think it is really remarkable the speed with which we're managing to start to move. I must admit, I think I've stopped 2 or 3 meetings this week to show people clips of blasting. So that's small things, I guess.
Yep. Yeah, small things, but actually big things. It's amazing to actually be moving Earth and starting to build our first nuclear test site. So this is going to be a ton of fun.
Absolutely.
And the site really is so beautiful. I mean, you look at the clips of the blasting going on, and you're like, I can't believe that we're actually like building a nuclear reactor here. This looks like an amphitheater, right? It's the mountains in the
Yeah,
background.
yeah, I know. It
We're
is a glorious part of the world.
So we had another exciting announcement as well, and that is that the Department of Energy announced that we've been accepted into the Advanced Fuel Line pilot program as well. So this is different than the pilot program to turn on a nuclear reactor by July 4th, but it's certainly in support of that. So there were also 4 companies selected to build advanced fuel lines, and that's actually part of
Yep.
what Mark is doing in South Africa right now. So why don't you tell us a little bit about that?
We didn't really advertise it, but let's talk a little bit about fuel. So, the critical path for a reactor clearly goes through fuel. We've got a reactor built effectively. We maybe need to use quotes for reactor. It's full scale, fully functional, sitting there behind Isaiah in Hawthorne. And so, really, what would take to make it a nuclear reactor is to add fuel. And um, to add fuel, you need to do a couple of things, right? So, the first thought we had was we would try biofuel. Buying fuel is hard. There are only a few suppliers who can make the TRISO we need. Um, so we realized we needed options. So when we conceived of Ward 250, we came up with a plan to both buy fuel and be able to make our own fuel. And that means that essentially we should be in a position by 4th of July to have 2 cores of fuel. One we've bought and one that we've made ourselves. And that means that at least we've covered our risks. So what I was in South Africa working with a local team in South Africa was the self-perform option, the make our own fuel option. The idea there was quite simple, that we have a team here who are performing engineering, and we're procuring both out of South Africa and Hawthorne equipment, which will enable us to make our own TRISO and to compact that TRISO into fuel compacts, which we can then load into our graphite blocks and put in the core. That sounds simple. That would, however, mean that we are one of the few people in the world making it. There are 2 or 3 other groups in the US who currently are set up to make TRISO, so we will join a pretty exclusive club. But really, for us, it was about the ability to control our own supply chain and be able to make things ourselves. and not be completely dependent on the market or availability, because the bandwidth of the available manufacturing is pretty small at the moment.
Yeah, that's absolutely right. And a few people have come to me and said, making trust is pretty hard. Why are you trying to do this? And I think it really just goes to show that Valar is serious. We're really serious about scaling this out and making a lot of reactors. We have a lot of power to make, and we're all going to need a lot of TRISO. Like
Yeah,
all of the people who are making TRISO today, we are customers. We'll continue to be customers, and we're going to have to make our own.
yeah.
There's not enough, and so this is really a whole of industry effort to actually bring nuclear fuel online at speed with commercialization, which is going to happen sooner than I think a lot of people expect. So yeah, this is us putting our money where our mouth is, that this is a really important piece of our plan, and we're willing to do the engineering effort to make it happen.
And just thinking about that, right? The only thing that's going to make it happen is people doing this. Isaiah, I saw an interview. I saw you on a podcast earlier this week, and it was basically the whole theme of your discussion there was that, right?
Yeah. Yeah. Just build it, I think, is the clip that you're probably referring to there. Yeah. I
Yep.
mean, everyone's known for, a couple decades, honestly, that it's time to make nuclear reactors smaller. And you have to make them smaller because it lowers the hazard and because it makes it easier to build and it lowers the capital requirements. So there's all sorts of factors, and people have talked about this for a long time. And what has been missing is people just building it, right? We have to
Yep.
actually get the team together, get the engineers, get the capital, get the site, build it, turn it on. And that really is the
So
guiding
so so
philosophy
TRISO
of how.
matters, right? And building your own TRISO matters. In terms of the just build it. And I guess if people ask why, right? What would we tell them?
We would tell them we need it and it needs to be built, right? That
Hmm.
you can't put fuel in a reactor with no fuel. So we have to.
Yep. And I think there's a lot around TRISO. Small gas cooled reactors like we're specializing in, like we're developing and deploying. Their whole safety concept is about building a super robust, bulletproof, indestructible, effectively fuel. That in a reactor like this, if we design the reactor right, or when we design the reactor right, is essentially inherently and intrinsically safe. There's the TRISO keeps all of the fission products inside the reactor, and essentially, if we set the reactor geometry and operating parameters right, we get to a point where we cannot get temperatures which damage the fuel and cause radioactive release.
Yeah.
Um,
Do you want to just give us like a quick doctrine of functional containment, Mark? Like, what are we really
yeah,
talking about here? I'm sure all the nerds are going to love this part, but like,
yeah,
what are we
functional
talking about? Why is
containment.
this
Yeah, I think this is definitely where we go viral, because functional containment is where it's at. But the idea is, I always like to think, like, let's roll back quite a long way, right? The nuclear doctrine in the U.S. Has always been about containment. So the reason why reactors are considered safe in the US is that even if they have the very worst conceivable reaction and the core melts and the coolant escapes, we've got this big pressure vessel, which is basically a concrete building, which contains all of the fission products, and we keep it all in one place and we can clean it up. And hey, we proved this at 3 Mile Island, right? And even more than that, the industry kind of doubled down on that story when Chernobyl happened, because Chernobyl didn't have containment. So that when the reactor, blew itself apart, I think is the technical term. The fission products all escaped effectively, and so now you have the situation where you don't have containment. Fission products get out, makes a mess. There's a huge cleanup. There's a lot of people exposed. So, the US industry doctrine has been, we have containment, this can't happen. Now, that means that since the 80s, a lot of the focus in regulation has been making sure you have a really good containment. But these things are really big and really expensive, and this drives you to bigger and bigger reactors because the cost of your containment is actually quite high. So, functional containment says, yeah, we've got containment. It's the containment function. It's not the containment building, right? And the idea behind functional containment is typically using something like TRISO, is that these little TRISO kernels, should have brought a handful from the
in the test lab?
from our test lab. Yeah, maybe okay. We'll insert some here. Okay. But these little kernels, they're tiny. They're about the size of the tip of a ballpoint pen, and each one of those is a pressure vessel that's incredibly tough, right? So pressure vessel toughness is, the amount of pressure a pressure vessel can handle is kind of governed by how thick the wall is compared to how big it is. And because these are so tiny, the walls are incredibly thick, and they're made of high temperature ceramic materials, which we deposit with sort of coating technologies. And essentially, you end up with these incredibly tough pressure vessels made of materials that can handle incredibly high temperatures. Um, and then there's lots of them. And so if you have even a small failure rate, it's only a few of these that sort of can potentially release their radioactive fission products that they contain. And that's the whole idea. So instead of building one big containment building, which has to work, we build millions of them, which have to work well enough, which
That's
is a
right.
lot easier.
Yeah, and I think there's sort of a concept here of separating out the risk into this is like diversification of risk, right? You're not
Yep.
concentrating all of your risk onto a single engineered structure, right? And if you
Yes.
got the containment dome wrong, you get the whole thing wrong, right? So we have qualification standards for our tracer fuel that they have to hit, and there's going to be a failure rate associated with that. And one of the things that's really interesting about diversification is that it's really, really hard to beat statistics. When you're in the millions, things
Yes.
generally behave, right? You can actually you can talk about future realities when there's a lot of different pieces, right? Whereas if you're it's very, very hard to say that this one object will never, ever, ever break. It's
Yep.
easier to say that this 10 million set of little kernels will have a certain failure rate that's within an acceptable boundary. That's actually something
Yep.
that's easier to say and to guarantee from an engineering standpoint. So I think this also goes back to our philosophy of lowering the hazard itself, right? When we talk about
Yes.
risk, talking about risk in terms of the, how bad it is times how likely it is, right? That's sort of risk. How bad would it be if it happened times how likely is it? One of the ways that we think about this problem is, well, let's actually make how bad it is less, right? Instead of
Yeah.
trying to make the how likely is it zero, let's try to make the how bad is it if it does happen zero,
Yes.
and
Yeah.
close to zero
Eliminate
if we can.
consequence.
That's right.
Eliminate
Yeah. So
consequence.
this is one of those ways that we can radically reduce consequence.
So I guess one of the questions that comes to mind is, is this a radically new idea, right? And
Mm,
and how much does it cost? And I think those are probably things worth exploring. So maybe diving into it. It's not a new idea. The
no.
first particle fuels started in the 50s, essentially in the UK initially, in the US and Germany. There was a collaborative project called Dragon, which was one of the first high temperature gas cooled reactors, which actually used these types of fuel. After that, 60s, 70s, there were a bunch of reactor demonstrations. The AVR in Germany, uh, Peach Bottom in the US, moving on to sort of ramping up of the technologies, 70s, 80s, with in Germany, the THDR, in the US, Forts and Vrain. And I think a lot of that technology development, it was always kind of second fiddle, even though gas cooled reactors were the first ones. But this new type of gas cooled reactor was not being pushed as seriously as the light water reactors. The economy of scale by mass production was, or not by mass production. So the economy of scale was basically pushing the technology that was the densest and could be pushed to the highest power the quickest, and that was favoring it. And that was before the first big accidents, the 3 Mile Island and Chernobyl accidents, right? And that kind
So
of changed
and
people's view.
just to clarify that, basically what you're saying there is that at the time the market was very focused on water reactors
Yeah,
with containment domes
yep,
because you could get very high power density there. And the market
absolutely.
was just interested in maximizing power density.
Yes. Now, and gas cooled reactors have never worked on that principle. So gas cooled reactors aren't new. The UK has had gas cooled reactors. Their reactors have been gas cooled reactors up until essentially in the 80s, where they built their first light water reactor. And they kind of work on a different principle. They kind of are the gentle giants, right? They're big, they're slow, they're low power density, and the idea there really is that you kind of get to a point where you don't challenge the fuel, and it's inherently or intrinsically safe. So and by designing that safety in at like a fundamental physical level, and that's the idea of functional containment as well, that you simplify your overall plant, you simplify your safety argument, and most importantly, you kind of create a limit to the worst case consequence that you can experience in nuclear safety. So that's the idea. But now what's interesting, right, TRISO. So TRISO, it started off as BISO, it started off with these little uranium kernels, and they started coating them. Eventually they were doing BISO. BISO is not as retentive. It's basically graphite, or porous carbon, and then pyrolytic carbon around. And then they figured they could put silicon carbide around it. And that's the start of TRISO fuel. And TRISO was essentially sort of the killer app, right, of fuel at the time, because this made this truly a little pressure vessel which could survive these, any reactor temperatures it was exposed to, and would basically keep all the fission products inside. Now, we talked about failure rate, right? And the failure rate started off okay, right? They were like 1 in 100,000, right? 10 to the minus 4 failure rate. But while the development of gas-cooled reactors as a technology kind of stalled after, in the 90s or the 80s, really what happened was that the development of TRISO continued. And in the sort of 80s and early 90s, the German TRISO was about the best quality in the world. The US TRISO lagged behind. Sorry, guys. But since then, there's been a lot of sort of global development, and the failure rates, the inherent sort of failure rate, the quality of the vessels went from, 1 in 10,000 or 1 in 100,000 failures to 1 in a million failures. So the quality of TRISO that we can produce today is essentially, these 1 in a million of these little kernels is there. So for every million kernels, we're only releasing fission product from one of them, right? And that means it's an incredibly clean fuel. And, even up until, the 2010s, mid-2010s, I would say we've seen, significant technology development and demonstration to a point where the NRC has essentially approved a recipe for TRISO with a strong expectation that if you can manufacture to this recipe, you will get really good, clean fuel.
So what is that spec? What spec are we trying to build here?
So there's two names for the spec, but the primary spec is what we call the AGR-12 spec. And that specifies both a TRISO and an encapsulation in a graphite compact. There's an AGR-56 spec. The TRISO is very much the same. The graphite compact is different. Compact. Well, we're going to have to edit that in. Edit in some T's there, guys. So the compact is different, but there were some challenges around the graphite compact. So the 1.2 spec is probably the best one. That's the one the NRC has reviewed and approved effectively, and so that's what everyone aims for. But wait, you ask, what does it cost? Right. And I think this is probably the next most important understanding, because it sounds like a killer app, but you have to understand that this is an incredibly expensive way to manufacture fuel, right? We're not just making pressing pellets and putting them inside a single tube, and welding the ends on the tube. We have to make, millions and millions of little pressure vessels. And this is done with sort of complicated thermal and coating processes and multiple steps. But our idea here as an industry, right, not just Valar's, is that that's a materials processing problem, and we can build up and improve the economics of that over time. And by putting
And what's interesting about that is that when you make a lot of a thing, you can drive costs down, right?
Yes.
And if you look at advanced materials processing, we're getting into the world of microelectronics, right? And microelectronics have shown over and over and over that the cost can be driven down dramatically with scale.
Yes.
So, we're doing pretty standard, chemical processes, right? There's chemical processes that drive many other industries. And in fact, a lot of the other industries have a lot harder chemical processes to do and process steps. So it's the type of thing where it's expensive today because we don't do it that often. We don't do it that often because there's not a big industry around gas reactors. But Valar has the commitment that we're making a big industry around gas reactors. We're going to make a lot of these. We're going to make a lot of the reactors sitting behind me and some bigger ones as well. And so we actually have the justification to say, well, we're going to make a lot of TRISO too, and it's actually going to
Yep.
become quite cheap.
Yeah. And
In the other, yeah, go ahead.
as I say, and by concentrating the cost in the TRISO, that gives us one place to focus, and it also makes the potential for using, you know, industrial grade, let me call it, components in the rest of the system and benefiting from the learning we can get there as well to drive the cost down, right? So,
Exactly.
and at the same time, drive the quality of our primary functional containment up.
That's right. It's sort of factoryizing a very,
Yeah.
very critical piece of the nuclear reactor and allowing some of the rest of the reactor to be a little bit overbuilt. Maybe that's one way to put it, right? We can afford to overbuild the rest of the reactor and we make our fuel the thing that we mass produce, right? And we can
Yep.
push that to very, very high spec and very high certainty, and we can get it very cheap and we can do it a lot. I like making millions of things. If you can make millions of a thing, you can generally get it to be cheaper, right? And it's going to be hard for us to make millions of reactors. So that's harder to control the cost in the reactor. But if you're making millions of tiny pressure vessels, that's actually something that sort of admits of factory scale. And so this is one of our ideas. Now, this is not just crazy ideas actually, because there is pretty good historical precedent of these costs being able to come down.
Yeah.
I've read some reports about prices of TRISO in the 70s and 80s, and they were somewhere around $5,000, $6,000 a kilogram, which is really not bad. It's really not bad. Some reports have China around those numbers today as well. And again, why
Yeah.
is that? Well, because they're doing a lot of it, right? China puts out a lot of TRISO, and so that the price is actually pretty reasonable. And I think we're going to do the same thing here.
It's possible, right? We know it's possible. Again, we've just got to do it.
We've just got to do it.